All right, mathletes, here we are going to be talking about relations and domain and range. So relationship is anytime we're trying to relate two sets of numbers. So here we're looking at relating weight of a package, okay, and the cost that it would take to ship it a fixed distance. Okay, so as we're reading this and we're looking here, we can see that if we have a package that weighs 2 kilograms, we follow the table on the left here for weights. 2 kilograms, well, this is strictly less than 2, so it doesn't include that one, but because it's included here at 2, we can see for a 2 kilogram package, it would cost $8. Okay, a 3.6 kilogram package falls within these two numbers, 2 and 5, so that too would cost $8. Okay, and for a 4.955 kilogram package, well, that's just below 5, so that too would also cost $8. So notice with this relationship here, we can have multiple answers, okay, which are the same answers for different inputs, because we could have any package that weighs between 2 and 5 kilograms, and then those packages would all cost $8 to send them. Okay? But a relationship is always linking two sets of numbers. Here it was weight and cost. So our next thing we can do is we can look at the graphs of here. So notice that with this relationship between weights and cost, remember that our first category was from 1 kilogram inclusive to a weight of 2 kilograms. So notice, because it was including at 1, we had a solid dot there, and because it went up to 2 but did not include 2, we had an open circle there. And notice that that structure followed throughout all of our step functions here. Okay, so we can see that a relationship is a set of any points which connects two variables. So the two variables here, we can see we have a relationship between these two variables. Okay, so another example here is we're looking at the cost of a statue compared to its weight. So our first example here, it asks for what are the variables? Well, the variables that we're dealing with are cost, okay, and our weight. Okay, which statue is the heaviest? So when I'm thinking about which statue is the heaviest, okay, I'm only looking at my weight axes, and I come over here and think of what one is the furthest right, and that's here. Statue E is the heaviest. Which statues are the most expensive? So that's dealing with cost. Okay, so I'm going up on my y-axis, which ones are the most expensive, and I see here that B and E have the highest cost of the statue. Okay, so which statue is the least expensive? Again, we're dealing with cost. Least tells me it's the smallest. So the smallest cost we're dealing with is the statue here, statue A. So here a graph is a good way to look at a relationship between two variables. Okay, so other types of relationships, here we can see this is a set of 5 points on this graph, similar to our previous example, and that's one way to look and think of a relationship. Okay, there's no equation connecting these points. Okay, we can't necessarily find an equation that's connecting these points. Okay, but we can list these points out. Okay, and see, all right, -3 is my x, 1 is my y, so I can see -3, 1 is there. And I can list out those points, and that's defining our relationship just with a finite set of points. Okay, well, remember, finite is limited. We're talking about a few amount of points. Well, what if we have an infinite amount of points? Well, here in example 2, we see we have a solid square, and the box is, and the relationship is everything within that square. Okay, well, that's an infinite amount of points within that box, but there is still restrictions on here. Okay, so we see that for our x's, okay, our x's are restricted from -1 to 0, okay, and our y's are restricted from 0 to 1. So as we kind of map out those restrictions, we see that we're going to get everything that is in this red box. So an example that I could have is some value with like a -0.5 and a y being 0.72. Okay, so I can see that would probably fall somewhere in there, and that would be an example of a relationship here. Okay, so other relationships are defined by equations. Okay, and in mathematics, these are typically the relationships that we deal with a lot in high school mathematics. Okay, so this relationship here of this parabola is defined by this quadratic equation here that is y equals -x squared plus 6x minus 5. Okay, so those, I can take any x value, plug it into this equation, and out pops a y value. I can do that with any value. So there's an infinite amount of values, and it's a set of all these points infinitely close together that go on to infinity. So there's a number of equations, but a graph's a convenient way of showing how those relationships are formed. Okay, and we can see one such relationship is when we put in an x value of 3 into our function. So I get -3 squared plus 6 times 3 minus 5 equals -9 plus 18 minus 5, which is equal to 4. Okay, that point, x being 3 and my y being 4, is a relationship. Okay, and 3 is related to 4 by this equation. Okay, so when we're looking at relationships, there's different ways that we can define them: points by points, within a bounded region, and on a curved line. Okay, so what is domain and range? Domain, okay, of a relationship is a set of all possible values that x may have. So when we're talking about domain, we're always wanting to talk about x. I always remember domain has the same starting letter as down. Okay, so domain and down, and x's always are downward axes. That is our x. Okay, our range values, okay, of our relationship is a set of all possible values that y may have. So remember, y is our vertical one. That deals with our range. Okay, so if we're looking at this function here, okay, defined by this straight line, it has a closed circle here that goes down to the point -5, -2, but does not include that point, so it's an open circle. And we want to define what is our domain and range. The notation is going to be important here. So when we do the domain of this, we're thinking about what are the possible x values it takes. So the furthest left that it gets is right here. It's bounded here. The furthest right that this function gets is bounded here. Okay, so this is from 1 to 5. But remember, it's an open circle at 5 here and a closed circle at 1. So how I'm going to always write this for domain, I'm always going to start with my x, and I'm going to put a bracket here to define my set. So it's a set of all x's such that, so a straight vertical line, that 1 is less than x, and x is less than 5, and I close my bracket. Okay, so those are going to be important when we're talking about domain. Now, when we're talking about our range, we think of this function, the lowest value that it takes is right here, and the highest value that it takes is up here. Remember, this is inclusive here when y is 3, but does not include this point down here because of the open circle at -2.
So just like range, I'm going to start with my set brackets, okay? And range always deals with y, and then such that my y is going to be greater than -2, but non-inclusive because of the open circle, but less than 3, including 3 because of the closed circle. Again, close the brackets, and that structure should always be the same when we're answering questions with domain and range. Okay, so let's look at some examples here. Okay, so for this one, we can see it's a parabola. Again, when I think about this, my domain is my x value. So I can see that this function, I'm assuming that all my turning points are graphed. So this function is going to continue, and it's going to continue going left forever and continue going up and right forever. Okay, so my x values have no restrictions. So as I write my domain, I put my bracket. Okay, I put x such that x contains all. Remember that that symbol is real numbers. Okay. And sometimes, so I usually write it like that. Okay, so that symbol represents real numbers. The range of this function, again, I'm assuming that this function is going to continue going up forever in this direction, but it has a basement. It stops here. Okay, so that range, the smallest that value ever gets is -1. It's a closed-in circle, so it's inclusive. So when I do my range, it deals with my y such that y is greater than or equal to -1, and closing my brackets. Okay, let's look at a couple more examples to wrap this up here. So A is similar to the one we saw before. Okay, so my domain, so I always do brackets x such that. So this graph's going to continue going left forever and right forever. So x's contained within my real numbers, pretty much everything. Okay, now my range, my up and down. So the range of this graph has a ceiling. It stops here. But again, I'm assuming that this graph's going down forever here. So the range of this, again, the formation is always the same, the set of all y, such that. So I have a ceiling. So the y's is going to be all values less than or equal to 4, because that's my y value. That's the max there. And I close my bracket. Okay. So again, range for my function, for the next one, b. So for my b value, I can see that my domain is going to have a leftward stoppage here at -4. Okay, it doesn't go any further left. Because of this arrow to the right, I'm assuming it's going up and to the right forever. Okay, so again, start with my brackets. So this is my domain for all real x's such that x's must be greater than or equal to -4. Okay, and close my bracket. Okay, now for my y's. Okay, so I have a basement here. I have a somewhere where this function is stopping. The lowest point is here at y being -6. But because of this arrow here, I'm assuming it's going to go up forever. So then my range is for all y such that y is greater than or equal to -6. Okay. Last function here is unique in the sense that it looks like it goes up and down forever. Okay. But it never crosses the axis here, so it never touches 0. Okay, and the same thing as it goes left and right forever, but it never crosses this axis here at 0. So then for my domain, okay, I have for all real x's such that x can't not be equal to 0, because here at 0 the functions never cross that axis but get infinitely close. Okay, we call those asymptotes. Okay, so because of this asymptote here, okay, with my y values, it never crosses there. I have, again, y's such that y cannot be equal to 0. Okay, so that's going to conclude our notes for tonight. If you have any questions, please bring them to class tomorrow.